Greetings, dear listeners and colleagues. Today I would like to present you specifics of designing and construction of a system for deep neural network generation. And it is known that machine learning models have been successfully used in researchers, business, in corporate management, device control, and more and more. And one of the most popular algorithms is deep neural networks, because use of one allows to solve a robust set of problems, from regression classification to a dimensionality reduction generation, and etc. But creation, training, and deployment of neural networks requires a particular intellectual resource, some mathematical programming skills. But in the context of globalization, Industry 4.0, and other factors, the use of custom DNNs should be more accessible to an average users and small companies, and that is why there is a need to study the necessary functionality for a system that would create neural networks for a user and create a project that devs can use to develop a software. First thing first, we should define some important terms in order to create a collective context, especially for main ideas like DNN. And we will start with the abstract highest concept, which is artificial neural network. So INN is a brain simulation system for the perception and analysis of information. Now, artificial feed-forward neural network is a system which take an input vector x, build some nonlinear function f of x to predict a response y. And now, within our paper, a deep neural network, DNN, is an artificial feed-forward neural network in which the topology of two sequential layers forms a complete bipartite graph. Okay, there is a little remarks. We assume that those networks use backpropagation as a training methods, and we will focus only on two main use cases of DNNs, regression and classification. And there are also several problems and difficulties when you're dealing with neural networks at every implementation stage. The common downside is the requirement of massive amounts of prepared data, which occurs at the beginning of the process. Then two central problems of the learning process are overfitting and underfitting. And one of the main drawbacks of the ready-to-use DNN is the lack of meaningful interpretation of its learned parameters. And when we are building a system that can generate a DNN, we would consider those problems that appear at the learning steps, which are over and underfitting. And that's why our information system should offer users some prevention mechanisms. And an advanced, effective way to stabilize learning and so prevent underfitting is an intermediate normalization of databases. And the problem of overfitting also have some classical approaches of handling it. For instance, we can make learning process a little bit harder over some difficulties, which will help to avoid forming some erroneous patterns in the networks. And one of the most common techniques for preventing overfitting with mentioned approach is a dropout. And often, a combination of three layers, dropout, batch normalization, and fully connected dense layer, which is called a composite layer, is used as a hidden and output layers of the network. And because of its real effects, our system uses them in a template DNN, an example of one you can see on the slide right now. And now we move into the next step of our presentation, which are the results of analysis of available solutions. Because DNNs entail an inherent advantages of traditional machine learning, they become very popular, and because of that popularity and power of DNNs, they have turned into a large numbers of information technologies that can help to create, teach, or deploy DNN. And we have allocated three types of systems to generate DNN. First one is frameworks, libraries, and so on and so forth, which require some writing of code. The second one is analytical platforms, which support the creation of multi-perceptrons or some other types of DNN. And the third one is specialized system for DNN creation. And we have tried to create a design and specific software for a system from the third type. And now, after we have defined some needed terms and components and allocated our system within the types we have created for solutions, we can move to the specifications and design of our system, starting from the overall concept. So conceptually, the design system generates a code scripts for DNN creating using TensorFlow and DNN itself, taking as an input data sets and preferred settings and configurations for DNN or its learning process, etc. After that, we can move to the object-oriented design with UML. So apparently the first created diagram is a use case. It contains some logically connected clouds of use cases, which are responsible for my functional part, from user registration to the learning of a DNN. Then the next diagram is the class diagram. Here we have tried to determine the minimum set of objects whose interaction and cooperation can fully perform use cases. And in order to show you a classical cooperation between those classes, we would like to present you a corresponding diagram, a cooperation one. And last but not least, the diagram that was presented in the paper is a component diagram. Within its context, we were able to unify the cross-platform and universal structure of a system software source code. And now, before we move to the creation of software, we've defined some requirements that must be met by development technology, which are the basic support of object-oriented programming. It's a speed of code execution and, of course, efficiency of writing and a class platform, because we need a unified code base for the main platforms, and that's why we have chosen Flutter as a development tag and Python's implementation of TensorFlow as a DNN creating and learning backend technology. And now, in order to prove that our design and specifics are usable, we have created a NeuroPIS system. And we would like to show here an example of its usage to create a DNN for a classification task based on a very popular first attempt dataset, MNIST. And from the first two screens, you can see a creation of a new project within our system. Then we move to the third screen. Here you can see an empty project, but on the fourth screen, we have loaded a dataset into the project. After the loading, you can see that the system set the parameters for the first and last layer of the neural network. And also we would like to show you how a user can reconfigure some settings, like the parameters of hidden layers or parameters for a training process. And you can see it from screen 5 and 6 respectively. And now on the last step, after all configurations are done, we can just run the project and see the results in the log widget, like you can see from this right side of the slide. From that point, I would like to briefly highlight a main findings of the work. Here we've tried to analyze the availability of DNN models for users in the forms of information systems, find its main limitations, shortcomings, in order to create design of more competitive system that can generate and teach DNNs. And in order to prove its relevance based on the given design, we've developed a system software. And with all said, I would like to thank all of you for your attention, and glory for Ukraine.